Welcome in, come on in, get comfortable. I was so glad you were joining us for this deep dive.
Absolutely. It is great to be here.
Whether you are actively prepping right now to, sit down and conquer the D-PSC-DY-23 exam, or you are just insanely curious about how these high-end enterprise data clusters actually work behind the scenes to keep the digital world turning.
And they really do keep it turning.
Right. Well, either way, this deep dive is perfectly tailored just for you.
Because enterprise data clusters truly are. The invisible engines powering so much of our daily lives, the architecture keeping them running smoothly, balancing massive workloads while preventing catastrophic data loss is just incredibly sophisticated.
It is, and our mission for today is laser-focused on that exact architecture. We are going straight to the source material to unpack 10 specific exam practice questions and their answers.
Yeah, the real core stuff.
Exactly. We're going to break down the technical facts, but more importantly, I think, we're going to look at the why behind the answers so you can truly understand the mechanisms at play.
Because memorization only gets you so far right. You really need to see the gears turning.
Spot on. But before we jump into the first scenario, could you lay out the basic facts of the D-PSC-DY-23 exam for us? Just so we all know the exact stakes we are dealing with here.
Sure thing. So if you are sitting for this exam, you are going to be on the clock for exactly 90 minutes.
Okay, an hour and a half.
Right. And in that hour and a half, you will face 60 multiple choice questions. Keep in mind, this includes both single answer and multiple selection formats.
Oh, so you really have to read the prompts carefully.
Absolutely critical. Missing a select all that apply will cost you. To pass, you need to hit a score of 63%, and the exam is delivered entirely in English.
Got it. Okay, let's unpack this. Rather than just throwing random flashcard facts at you, we're going to trace the actual journey of data through a cluster. Let's start at the very edge of the system, right where a user first tries to connect.
The front door, essentially.
Exactly. One of the practice questions throws a scenario at you regarding SmartConnect load balancing. It asks how the system distributes client connections when it's specifically looking at the current number of active sessions on each node.
Right. And when you see that set up on the exam, the policy they're pointing you toward is the connection count policy.
Connection count.
Yep. Rather than just using a basic round-robin approach, the system actively tallies up the active sessions and directs the new connection to whichever node currently has the fewest.
Which seems like common sense. I mean, why is that distinction so critical in an enterprise environment? Because a lot of legacy systems just use that round-robin method where they go down the line, giving one connection to node A, the next to node B, the next to node C, and so on.
Well, round-robin works fine in very simple environments, but it has a major blind spot.
Which is?
It doesn't account for how long a connection stays active or how heavy the workload is. Think of a restaurant host assigning tables to servers.
Okay, I like this.
If the host just goes in a strict circle, giving table 1 to server A, table 2 to server B, table 3 to server C, they might not realize that server A's table is a party of 12 who are going to sit there for 3 hours.
Oh, right. While server B's table was just 2 people who quickly grabbed a coffee and left.
Exactly. So if the host keeps strictly to the circle, server A gets overwhelmed with another massive party, while server B is just standing around with an empty section.
That makes total sense. So the connection count policy turned SmartConnect into a highly observant restaurant host.
You got it. It actively surveys the landscape at that exact millisecond, sees who has the lightest current workload in terms of active sessions, and routes the new incoming connection right there.
This is absolutely critical because it prevents individual nodes from becoming choked or overloaded while other really expensive hardware just sits idle.
It maximizes your hardware investment beautifully.
Okay, so we have the front-end traffic flowing smoothly, and our nodes aren't choking. But enterprise clusters aren't just serving client data. They're constantly running internal maintenance.
Oh, constantly.
Which brings up question 9 from our stack. This shifts the focus to those background tasks. The exam asks which job engine impact level should be selected to ensure a background task has the least possible effect on client operations.
And the answer you need to know for this one is the low impact level.
If we connect this to the bigger picture, an enterprise storage cluster is essentially a bustling metropolis, right?
That is a great way to look at it. You have the main commerce happening, clients reading and writing files, but you also need massive infrastructure maintenance happening in the background to keep the city functioning.
Like fixing the subways or repairing the roads.
Right. And the job engine handles those background maintenance tasks, like rebalancing data across the cluster or running heavy antivirus sweeps.
But you obviously don't want a massive data rebalancing job consuming all your processor power right when your finance department is trying to pull their end-of-quarter reports.
Which is exactly why the impact levels exist. When you configure a background job's impact to low, you are actively restricting how much CPU, disk I/O, and network bandwidth that specific task is allowed to consume.
So it forcibly lowers the job's priority within the cluster's operating system.
Precisely. The maintenance task still gets done. It just slowly chugs along in the background, only grabbing resources when there is a lull in front-end client activity.
That ensures that normal client operations remain fully responsive. The users on the front end shouldn't even notice the maintenance is happening.
Which protects the business's overall productivity. No one is complaining about lag.
Now, even with perfect traffic management and quiet background maintenance, we have to face the physical reality of data centers. Hardware breaks.
Always. It is never a matter of if a hard drive fails, but when.
Exactly. And the exam addresses this directly in question 3. It asks, in a cluster configured with N+2 protection, what is the maximum number of simultaneous drive failures the system can sustain without data loss?
The critical answer to remember here is 2 drives.
2 drives. This is a foundational concept in storage architecture, isn't it?
It really is. The N essentially represents your actual raw data, and the +2 represents the mathematical protection overhead.
So in an N+2 protection scheme, the system calculates and stores 2 additional parity blocks for every single data protection group spread across the nodes.
That is exactly right.
For those trying to visualize this, those parity blocks act essentially like an algebraic safety net, right?
That is a highly accurate way to look at it. Because you have 2 mathematical safety nets, the cluster can tolerate up to 2 simultaneous drive failures within that specific group without losing a single byte of data.
It just rebuilds it.
Yeah, the system uses the surviving data chunks and the parity blocks to mathematically reconstruct whatever was lost on the dead drives.
But there is a catch there, isn't there? It becomes a race against time once that first drive drops.
It absolutely is a race. If you lose 2 drives, you are operating in a degraded state. The system immediately starts rebuilding that missing data onto available spare space.
And if a third drive fails?
Well, if a third drive fails within that exact same protection group, before the system has had time to completely reconstruct the data from the first 2 failures, you cross into the danger zone.
Because you have exceeded your +2 safety net.
Exactly. And at that point, the system might not be able to recover that specific stripe of data.
Wow. That makes drive rebuild times a truly critical performance metric.
Huge.
And speaking of failures, question 8 deals with a completely different nightmare scenario. A total loss of power.
The ultimate stress test.
Right. The question asks, what hardware component in the Gen 6 architecture is specifically dedicated to storing the file system journal to protect data during a power failure? And the correct answer is dedicated internal flash drives.
This raises an important point, though. Why do we even need a journal sitting between the active memory and the hard drives in the first place?
The question.
When a cluster is processing thousands of operations a second, it doesn't write every single change directly to the spinning disks instantly. That would be far too slow. It holds them in a high-speed temporary cache.
But if someone trips over the main power cable in the data center,
everything in that temporary cache vanishes instantly.
That is terrifying.
To prevent massive data corruption, the Gen 6 architecture uses a file system journal. Think of it like a black box flight recorder on an airplane.
Okay, a flight recorder.
Every single pending file system operation is quickly logged into this journal before it is officially committed to the main storage drives. By storing this journal on dedicated internal flash drives, which do not lose their data when power is cut, the system ensures that these transaction records survive the outage.
So when the power is finally restored and the cluster boots back up, it just checks the flight recorder.
Exactly. It sees exactly which writes were interrupted mid-flight and simply replays them from the flash drive to maintain complete data consistency.
It guarantees that your file system doesn't tear itself apart during an ungraceful shutdown. That is incredible.
It really saves the day.
Here's where it gets really interesting, because question 2 shifts us from physical hardware failures to logical data protection. It asks how the file system handles data modification when a snapshot of a file exists, ensuring the snapshot remains unchanged.
A very common scenario.
And the exam answer is that the system writes the new data to a new block and keeps the original block for the snapshot.
This mechanism is known as copy-on-write, and it solves a massive storage problem.
How so?
Let's say you have a massive 1 terabyte database file, and you take a snapshot of it at noon to protect against accidental deletions. A snapshot isn't a completely separate, duplicate 1 terabyte file.
Right, because doing that every hour would bankrupt a company's storage budget.
Exactly. A snapshot is really just a microscopic map of metadata pointers saying, at noon, the data lived on these exact blocks on the hard drive.
But what happens at 12:05 p.m. when a user updates a single row in that database?
Yeah.
If you overwrite the original block on the drive, you've completely ruined the noon snapshot. It no longer reflects the state of the data at noon.
Which is why the system intercepts that write command. Instead of overwriting the original data, it takes the brand new data and writes it to a completely empty, newly allocated block elsewhere on the hard drive.
Ah.
So the original block, the one from noon, stays frozen in time, completely untouched.
Wait, if it's writing to a new block every single time I make a tiny edit, doesn't that inherently fragment the live data file over time?
It does create some level of fragmentation, yes, which the system's background processes have to manage eventually, but the trade-off is absolutely worth it.
Because the snapshot is perfectly preserved without needing to duplicate the entire file.
Right. And the live file simply updates its internal metadata map to point to the newly written block. It allows enterprises to take thousands of snapshots, providing granular recovery points without instantly consuming all their available storage capacity.
Preserving data is essential, but it eventually forces administrators to deal with expanding space. Which brings us to question 7.
Data lifecycle management.
Yes. The exam asks which feature allows an administrator to automatically move data between different storage tiers based on specific criteria, such as the age of the file. And the answer you are looking for is file pool policies.
In the enterprise world, storage is a tiering game. Not all data provides the same immediate value to the business.
Right, you have your hot data.
Active projects, virtual machine disks, live databases, those need to live on your fastest, most expensive flash storage nodes so users don't experience latency.
But then you have cold data.
Exactly. Think of old compliance records, raw video footage from 3 years ago, or completed architectural blueprints.
You definitely don't want a 3-year-old video file clogging up the expensive flash drives that your active database needs to run smoothly.
File pool policies solve this by allowing administrators to set up automated rules engines. You can configure the system to monitor the metadata constantly.
So if a file hasn't been accessed in over 90 days,
the policy automatically and seamlessly migrates it from the high-performance flash tier down to the slower, high-capacity, and much cheaper spinning disk archive nodes.
that is brilliant.
Yeah.
And you can base these rules on file age, file size, specific directory paths, or even specific project tags, right?
Any of those criteria. The automation is the real value there. You don't have an IT guy manually dragging and dropping folders every Friday night.
But what happens when even those massive spinning disk archive nodes get full? Because question 6 addresses this exact scenario.
The cloud tiering question.
Yes, it asks what happens to the file data on the local cluster when a file is fully archived to a cloud target. The answer is that the actual data is deleted locally and replaced with a small pointer file.
When you exhaust your physical data center footprint, you turn to the cloud. To physically free up that local space, the actual bulky data completely leaves your physical cluster.
It gets encrypted and shipped off to an external cloud storage provider like AWS or Azure.
Exactly. But to keep the user workflow intact, the system leaves behind a tiny pointer file, often called a stub.
It's sort of like a library card catalog system. You pull the card, it has all the details of the book, but the actual physical book is stored in a massive offsite depository somewhere else.
That is a perfect analogy. The beauty of the stub file is that it looks exactly like the original file to the end user. It retains the same file name, the same permissions, and the same icon in their file explorer.
So if a user double-clicks that stub 6 months later, they don't get an error message or have to call the help desk.
Not at all. The cluster's file system intercepts the request, reads the pointer, reaches out to the cloud, automatically pulls the data back down, and opens the file.
Wow.
There will be a slight delay as it downloads, sure, but the retrieval process is completely transparent to the user.
It effectively gives the cluster a limitless ceiling for archiving without disrupting how people actually work.
It is incredibly powerful.
Okay, so now that we have the data stored, protected, and tiered, we have to control who actually gets to look at it. Our final theme covers user identity, access, and limits. Question 4 deals with a very common protocol headache in IT.
The translation problem.
Yes, it asks which service is responsible for ensuring that a user has a consistent identity when accessing the cluster through different protocols, specifically like SMB and NFS. The correct answer is the identity mapping service.
What's fascinating here is the absolute language barrier that exists between different operating systems in a modern enterprise network.
A language barrier.
Let's say you have a developer, let's call him David. When David logs into his Windows workstation and accesses a file share using the SMB protocol, the Windows Active Directory identifies him using a long string of numbers and letters.
A Windows SID, right, a security identifier.
Exactly. But David is a developer, so later in the day, he might SSH into a Linux server and try to access that exact same storage cluster using the NFS protocol.
And in the UNIX world, over an NFS protocol, the system doesn't know what a SAD is.
Right. It only identifies David by a completely different number, a UNIX UID, a user ID.
So to the storage cluster, it looks like two completely different entities are trying to access the data.
Precisely. If the cluster thinks they are different people, it will likely deny the Linux user access to the files created by the Windows user, causing major workflow friction and denied permission errors.
Which is where the identity mapping service steps in to save the day. It acts as a universal translator at the cluster level.
A perfect description.
It takes the Windows SID coming in via SMB and the Unix UID coming in via NFS, ties them together in a database, and says, hey, regardless of the protocol, these both belong to David.
It ensures that the exact same user gets a consistent identity token. This guarantees that the correct security permissions and file ownership are applied flawlessly no matter what machine they are logging in from.
That prevents a massive amount of help desk pickets, I am sure.
You have no idea.
Now, taking access control to a much larger scale, what if you have entirely different organizations trying to use the same physical cluster? Question 10 asks which feature allows for multi-tenancy by providing isolated namespaces and separate authentication providers on a single cluster.
And the exam answer here is access zones.
Access zones. This is a massive feature for compliance and cost saving, isn't it?
Huge. Imagine a large regional hospital network. You have the clinical side dealing with highly sensitive patient health records governed by strict IPA regulations.
Right.
On the exact same campus, you have the hospital's HR department dealing with payroll and maybe a public-facing research department. They all need high-end enterprise storage.
But for strict regulatory and privacy reasons, the HR department cannot even be allowed to see that the clinical patient directories exist, let alone access them.
Buying 3 separate multi-million-dollar physical storage clusters just to keep the data separate would be an incredibly inefficient use of capital.
So access zones solve this by allowing you to partition a single physical cluster into multiple logically isolated virtual environments.
Exactly. Each zone acts like its own independent storage system with its own distinct namespace.
Meaning the file paths and directory trees are completely walled off.
Yes. Each zone has its own dedicated directory service, its own authentication provider, and its own routing logic.
So when a doctor logs into the clinical access zone, they only see the clinical namespace.
They are completely blind to the HR data, and their authentication traffic never even crosses paths. It provides true multi-tenancy, allowing organizations to maximize their hardware investment without sacrificing an ounce of security or regulatory independence.
That is just elegant engineering.
Yeah.
All right, that brings us to our final question, question 5. It deals with managing user behavior.
Always a fun challenge.
The exam asks which quota setting only tracks storage usage and notifies the administrator without actually preventing the user from writing more data to the cluster. The correct answer, an advisory limit.
Storage administrators absolutely need to keep an eye on capacity, but they also have a mandate to keep the business running smoothly. You have different types of quotas at your disposal.
Like a hard limit.
Right, a hard limit is a strict boundary. If you place a 500 gigabyte hard limit on a project directory, the moment a user tries to write byte number 500 gigabytes in 1, the system throws an out-of-space error. The write fails.
Which is fantastic for strictly controlling physical space, but could be disastrous if a user is in the middle of rendering a critical 4K video project for a client deadline. The system just stops them cold.
Which is why an advisory limit is often the preferred tool for monitoring. It acts as a softer approach.
It constantly monitors the directory's threshold, and when a user crosses it, it quietly generates an alert or triggers an email to the storage administrator.
It says, the marketing department is using way more space than we forecasted.
It is the check engine light of data quotas.
Exactly.
It tells the admin to investigate before the system completely runs out of space, but it stops short of strict enforcement. The user's workflow isn't interrupted, the video finishes rendering, but the IT team now has the reporting data they need to go have a conversation with that department about archiving old projects or increasing their storage budget.
It bridges the gap between IT enforcement and business continuity.
Thank you so much for joining us on this deep dive today. Keep studying, keep exploring the architecture behind the answers, and never stop questioning the systems around you. We will catch you next time.